This video is about absolute or global extreme values. Those words can be used synonymously. Different authors will prefer different ones. They mean the same thing. We'll start our notes with a definition. We're going to let c be a number in the domain of the function f. Then f of c is possibly an absolute or global maximum value of f if f of c is greater than or equal to f of x for all x in the domain of f. You'll notice the distinction here between the definition of the relative or local maximum that we did previously. Now it's for all x. That's what the global or absolute connotates in this case. Or secondly, that this value f of c is an absolute or global maximum value of f if f of c is greater than or equal to all f of x for all x in the domain. Note, absolute extrema will not occur at the boundary of an open interval. Next, we'll consider the extreme value theorem, which states if f is continuous on a closed interval from a to b, then f attains an absolute maximum and an absolute minimum value on the interval. So what this theorem guarantees is that we can find an absolute max or min on a closed interval as long as the function is continuous. Now, how we find these absolute mins and maxes matters, and there's a closed interval method for doing this, for finding the absolute or global extrema on a function and an interval. To find the absolute or global maximum and minimum values of a continuous function f on the closed interval from a to b, we'll use the following few steps. First, we'll find values of f at all critical numbers. We discussed critical numbers in a previous video. We're going to pull that definition back into play here. Secondly, we're going to find values of f at the endpoints of the interval. So we have some closed interval given here from a to b. We're talking about finding like f of a and f of b. Those would be the values of f at the endpoints. And then thirdly, once we do all of that work, the largest of these, from all the values we found in steps 1 and 2, is the global or absolute max, and the least is the global or absolute min. Let's try an example where we want to identify any extrema, local or global, relative or absolute, in the following graph. Now, this graph is drawn, and let's see if we can describe it and then dive right in. F of A is a solid dot, and then there's an increasing kind of curve that bends downward to the right, but it's still increasing all the way up to where we find f of b at the top of that little piece of the graph. Directly below f of b, where there's a solid dot at f of b, below it there's an open circle starting another piece of the graph, which has a similar shape, increasing but kind of bending downward to the right as it goes up, until we hit a circle at the top of that piece, which is directly above c, the input. And then f of c below that open circle is a solid dot, which is starting another piece, which just kind of swoops downward to a valley at f of d, and then spikes up to a sharp point way at the top at f of r, and then it kind of plummets downward from that sharp point, decreasing but kind of veering off to the right until we hit a solid point at f of s. Now, our goal with this picture is to be able to apply all the definitions that we now have for our extrema, both local or global, and identify which of these x values and their corresponding f of x values would qualify as any of them. It's not that we're going to use every one of the x values located on this x-axis, but we may use any of them to define these local or global extrema. We'll begin looking at the value a. There's a spot labeled a on the x-axis, and you'll notice that the output there, f of a, is a solid dot, and if you just kind of glance across this graph, the y-coordinate of that seems to be the lowest point on this function that is graphed, which means, and since it's a solid dot, we can call f of a the absolute min. It's the smallest value for the entire function on the entire domain. Notice we used f of a to represent this absolute min. Remember the extreme values are y coordinates or output values, so f of a is the absolute min, not a. A is just where it's located on the x-axis. Sometimes it's good to try to find the global or the absolute extrema first. So there's the absolute min. If you kind scan through the graph, I think we'll be able to find that f of r would be the absolute max. Again, if you look at where r is, it's at the very top of that peak. That's where we find f of r, and that does appear to be the highest value on this function's entire domain. So we could say that f of r is the absolute max. It's higher than any other function value on this graph. Now moving on to the local or relative mins and maxes, these can be a little trickier given the definition because, as you may recall, the relative or local extrema are defined on an open interval, and we use that language in the definition of that video where we said near some value, and near meant an open interval. So these can be a little trickier. Now let's start by trying to find a relative or local min, minimum value. What we're looking for is some part of this graph that within an open interval that we could draw or imagine has the lowest value. So you may look at the absolute min and recall, we already said that's f of a, but you may recall the definition we used for our local or relative min, so that it could not occur on the boundary of a domain like this or a closed interval, because you can't actually put an open interval around a. It's a closed boundary with a solid dot, which means there's nothing to the left of it. So it doesn't quite fit that definition. We've already used f of a as the absolute min. Let's just consider some other options here. If you look at b, notice that f of b is an open circle, and you may say, well, it seems to be like the lowest place within this piece of the graph that it's connected to. The problem with it, though, is that if you were to try to put an open interval surrounding b and kind of extend where that open interval would go vertically, it wouldn't be such that f of b is the lowest within an open interval, because first of all, f of b is actually up at the solid dot above that open circle, and so it wouldn't qualify for a relative min at b. Now you may say, well, maybe f of b is a relative max. Now that could be, because if you look directly above the open circle, okay, where x is b, we see f of b is the solid dot, which is kind of like the end of that first curving piece of the graph. Well, if you look surrounding that in this open interval that we've kind of dashed our way upward vertically to see where it is, then it does appear to be the highest value of the function within that open interval. It's certainly the highest in the piece that it's connected to at the end, and then as you drop down to the next piece, it's even the highest from where that would continue, which is like the right side of the open interval we've now drawn around b. So we actually could say that f of b would be a relative or local max. Now if we move along to c, the value c on the x-axis, this is where, as we saw earlier, the second piece of the graph, which is this upward bending, curving, increasing piece, has an open circle straight above c, which means f of c is actually this solid dot that starts the third piece of our graph, which is this kind of mountain peak looking piece. So f of c is actually the solid dot directly above c. Now you may wonder, well, is that a relative extreme value? We already know it's not an absolute. We've already defined the two absolutes we have. So we may say, well, if I could draw an open interval surrounding c, what's happening above that? Well, if you extend that open interval upward, which I'll do with some dashed lines, you can see that within that span, it doesn't appear that f of c is relatively or locally a highest or lowest value. If you go to the left of it, to the left of c, kind of like in the open interval spot to the left of c, you'll find that directly above that there actually are higher values. So we wouldn't say that it's a relative max. It's not the highest within this little span of open interval here, but nor is it the lowest, because to the right of c the graph actually goes lower, which means it's neither. So we could actually put that down. Let's say f of c would be neither, or we'll just say none. It's not a relative or global, a local or global extrema. Now as we move along to the right here on our x-axis to the next value, which is d, we'll look above and find that d seems to be at the valley of this last mountain-shaped part of our graph, which means if I were to throw an open interval around d and follow it upward to the graph, it does appear actually that f of d would be at the valley of that graph, which seems to be then the lowest point within that open interval, which means we could call that value a relative or local min. So f of d, the y value there, is the lowest value within this open interval that we could draw surrounding it, which means we'll call it a relative or local min. Moving on to r, we've already discussed that f of r is an absolute max, but interestingly, that also fits the definition of a relative or local max. So since f of r is the highest value in the entire domain, it's an absolute max, but if I were to draw an open interval surrounding r and kind of follow that open interval upward, it does seem that that still would fit the definition as in the highest value within that open interval surrounding it, which means we can go back to f of r and say not only is an absolute, it's also a relative or local max. It fits both definitions. F of r is both an absolute and a relative max, or you could see a global and a local max value. And lastly, moving to the right to our value s, located on the x-axis, directly above it we have the end of our graph. It's a solid dot at the end of the mountain that's kind of swooping downward to the right. And you'll already recall that we know that's not the absolute min because it's not quite as low as f of a. We already talked about that when doing the absolute min. But also recall for the definition of relative or local minima, which you may be suspecting at f of s here, those cannot occur at the boundary of a domain like this that's closed, because you can't actually put an open interval around it that's within the domain. The domain stops hard at s. So there's no way to put an open interval around it because there's nothing else to the right of it, which means we're not going to call it a local, which means this will be another none. We'll just say f of s is none, just like f of c was none. So a visual problem like this can get a little crazy, the picture can get a little messy, but sometimes you have to kind of mark on it, keep your definitions near you, and test them piece by piece to know, do the places located on this graph actually fit the definitions. Let's try an example where we want to find the absolute extrema for a function given as f of t equals t minus the cube root of t on the closed interval from -1 to 4. So we have no graph of this function, we're just looking at the algebraic definition of it, but we want to find absolute extrema. Well, you'll recall from our notes above that there's a way to do this, there's a method for doing that. We want to do two things. First of all, find f of c for all critical numbers defined as these c values. So we want to find the critical numbers of this function and evaluate it at them. But then secondly, we want to find f of -1 and f of 4, those coming directly from the boundaries of this closed interval. So this is in keeping with the method we defined above in our notes. It kind of nicely simplifies the process to just a couple steps. So first of all, let's see if we can find out our critical numbers, which is a process we've done already. By definition, we know how to find those. That is when we find the derivative of the function and then set it equal to 0 or find where it's undefined. Well, let's take a second then and find f prime of t, since we're going to need that anyway. F prime of t, if we use the definitions or the methods we have for finding derivatives already, we could say the first term derivative, it was just a t, that's at 1. Okay, minus, and then the cube root of t is really t to the 1/3 power. So we could use our power rule and say minus 1/3 t, the power comes down in front, and then we decrease that power by 1. Well, it was 1/3, take away 1, and you get negative 2/3. So we have negative 1/3 t to the negative 2/3, and that's the second term of our derivative. Now, we may want to clean this up a little bit since we'll be using it to find other things, and we want it algebraically, I guess, prettier than this. So you could write this as, if you find a common denominator, it'd be 3t to the 2/3 minus 1 over 3t to the 2/3. That's just doing a little algebra there to get a common denominator. That's what we'll want to use for our derivative when finding like where it's 0 or where it's undefined. Let's now try this for the critical numbers. We want to first find out where is f prime of t equal to 0, if anywhere. And again, with a fraction defined as f prime of t here, that would be true when the numerator is 0. So that would mean like 3t to the 2/3 minus 1 equals 0. That's just the numerator of our derivative that we found, which means 3t to the 2/3 equals 1, which means t to the 2/3 equals 1/3. If we solve for t by raising both sides of this now to the 3/2 power to undo that 2/3, we'd end up with t on the left side equals 1 over 3 to the 3/2. But the process of doing that step right there would involve taking a square root of both sides. That's what this 1/2 power actually does, which means we do need a plus or minus in front of it. Okay, there's a little bit of algebra there lurking that I didn't write, but you could probably write out those steps just to be clear if you'd like. And then we could simplify this a little bit further to call it plus or minus 1 over 3 root 3. Again, a couple steps of some algebra or really arithmetic there to confirm that. Okay, so t is equal to plus or minus 1 over 3 root 3. If we rationalize that, we would get plus or minus root 3 over 9. Again, maybe write out a step or two for rationalizing if that's not super clear, but that's all we're doing there, which means, okay, let's keep in mind the context. When t is plus or minus root 3 over 9, that's when our first derivative is 0, which means we potentially have some critical numbers here. We have to go check to make sure that those are in the domain of our function. Now, the way the function's defined actually has a domain of all real numbers, given f of t above, but we're kind of narrowing or zeroing in on this particular closed interval from -1 to 4. So we really want all that we're doing to be within that closed interval. These values of plus or minus root 3 over 9, if you were to estimate them on a calculator just to be sure that they are, we get plus or minus 0.19, which, yes, definitely falls from -1 to 4. So, okay, we have t values here that occur for when f prime of t is 0, and they are within the domain of our function, which means these values, plus or minus root 3 over 9, would be qualified as critical numbers. Okay, so we're going to keep that in mind. That's part of what we're doing. We're going to keep it in exact form, even though we may have to use a calculator to estimate some things. Let's leave those as they are for now. That's only one way we could find critical numbers. Our second option would be to know or find, is f prime of t undefined anywhere? As we've discussed with critical numbers, they occur when the derivative is 0 or possibly when it's undefined. The answer to that question is actually it could be, because the denominator of it, of this derivative function that we've simplified, has this 3t to the 2/3 power in it. So when t is 0, we're dividing by 0, which would make it undefined. And of course, 0 is within the domain of this function. It's within this closed interval, so it actually counts as a critical number as well. All right, so we have actually three critical numbers because of the plus or minus for the first option we got. So we found the critical numbers. That's really step one. We want to find f of c, though, for all of them. We need to evaluate the function at those values. So we'll do that. Let's at least write that out a little bit. So we have f of 0. That would be for this critical number we just found. We also want to find f of root 3 over 9. And then f of negative root 3 over 9. That was from those first option critical numbers we had found. That's what we want for step one in this process of searching for absolute extrema. The rest is just step two, which is finding the function evaluated at the endpoints. That would be f of negative 1 and f of 4. To find the absolute or global mins and max of this function, all we need to do is evaluate all of these places from step 1 and 2, and then compare them. The greatest one's the absolute max, the least one is the absolute min. So we can estimate as needed here. F of 0 should be 0. F of root 3 over 9, estimated on a calculator, would be negative 0.3849. F of negative root 3 over 9 could be estimated on a calculator as 0.3849, but positive. F of negative 1 should be 0, and f of 4, estimated on a calculator, should be 2.413. Okay, so we are estimating, and by that I mean rounding these decimals, but that's enough to know which one is highest and lowest. That's all we really need here. As we now scan through this list of options, we'll notice that the least or lowest value is f of root 3 over 9. That was the negative 0.3849. So we'll call that our absolute min, or you could say global min value based on all comparisons. And then similarly, the highest value in our list would be the f of 4. So we could call that the absolute max. That's where we estimated 2.413. And so the process of finding an absolute or global min and max is simply getting this list and finding the highest and lowest like we just did.